of space tourism itself. ISS is located inside Earth's magnetic field, so it enjoys a degree of protection right now. But future astronauts en route to the Moon and Mars will be outside this magnetic bubble, and their spaceships are going to be in direct contact with the sun's atmosphere. Impacts on technology, another one. This could be a multi-trillion-dollar impact depending on the technology sector. Space systems, communications, navigations, ground infrastructure like power grid. More than 500 active satellites circle the Earth, and we are adding to it every day. We rely on them for TV, telephone, internet, GPS, navigation, and weather forecasting. All are vulnerable to space weather. And of course, let's not forget terrestrial climate, both short and long term. The next slide literally kind of describes the domain of heliophysics as the heliosphere itself, which stretches from the bright core of the sun to the dark void 5 billion miles beyond Pluto, where the sun's magnetic field piles up against the plasma clouds of interstellar space itself, the domain of astrophysics. But in the next slide, let's think about it more. It's just not solar magnetic field that's important. A planetary magnetic field makes a difference too. On the top panel, what you see is that Mars, we believe, lost its global magnetic field, removing the planet's main source of protection from solar wind. So Mars's atmosphere is getting pummeled by about 1 million miles per hour solar wind, traveling almost 0.15% the speed of light. This provides enough energy to the particles to escape Mars's gravity. Mars presently loses about 100 grams or 1/4 pound of atmosphere every second. And this number goes up by a factor of 10 or 20 during a solar storm. In the lower panel, of course, I'm talking about, our hunt for habitable exoplanet. And what we are showing there is a simulation using models developed in heliophysics to show a red dwarf with large spots, rapid spin rate, and deep convective zones that's supercharging its space weather environment and causing the nearby exoplanet's atmosphere to strip off, affecting the ability of a planet to support life. That's what we do in heliophysics. Ultimately, in the final slide, I give a picture of the heliophysics ecosystem as seen from the lens of FDL. So remember, we've been doing this for 3 years, and heliophysics is a unique hybrid between meteorology and astrophysics. Continuing on that theme, our meteorology topic this year is tracking geoeffectiveness of solar storms with multidimensional data and space situational awareness. And the question, can we use ML to understand and forecast complex impact of solar storms on terrestrial technological systems, as I just showed? Or could we use ML to improve our ability to globally monitor geomagnetic storms? On the astrophysics side, the question becomes, can we extract stellar features from exoplanetary transits for understanding, forecasting, and prediction of these exo worlds? And the question, can we use applied AI and machine learning tools and processes to Kepler and test data to identify and define the properties of star spots, stellar rotation, and stellar magnetism in tens of thousands of stars, and both increase our understanding of our own star, sun as a star, and inform the habitability conditions created by that host star? Thank you, and I'd like to pass it on to the teams to talk about their results now.
Thank you. Hello, this is Bashi from Geoeffectiveness team, and here I'm along with my teammates, Vishal from India. I'm located in Boston, and Theo in UK, and Panos in Greece, and our amazing team, Asti, Mark, Ryan, and Sida, located in California. We always say sun never sits on our team because we cover all over the globe. Have you ever been in a blackout? Now imagine a blackout, a train signal failing, an oil pipeline catching on fire, communication disruption all at the same time. Each one of these can be caused as a result of the interaction between the sun and the earth. Most of the time, this interaction manifests itself as the beautiful northern lights, or known as the auroras. But sometimes the sun has solar storms and emits bundle of the plasma known as coronal mass ejection. And when they encounter the Earth magnetosphere, they change the configuration and they can induce currents to the system. These geomagnetic storms are not rare events. In fact, they happened many times previously on the Earth. But we were lucky that the most of these extreme cases to date occurred during the time that we were less dependent on technology. For example, Carrington event in 1859, during which the telegraph system, the only technology we had back then, was in fire, and aurora was observed as south as Cuba. And in 2012, we had similar coronal mass ejection, and our satellite, the Stereo 8 around the sun, was able to detect that. Thankfully, it went ejected in the opposite direction of the Earth. But imagine if it faced the Earth. The National Academy of the Science estimated that if that CME faced the Earth, it would have devastating economic impact on the Earth. So now the big question is, can we be prepared for such geomagnetic storms?
The answer is that yes, we can. Just as we produce space weather forecasts, we can also produce space weather forecasts based on measurements of the solar wind and the magnetosphere. But the challenge is that the disturbances start out on the sun, 94 million miles away from the Earth. The solar wind conditions are measured at a single point between the sun and the Earth, and we finally observe the effect sparsely on the ground after the information from the solar wind has been heavily processed by the magnetosphere. Our task, and the overarching problem, is to connect this complex set of dots we have between the sun and the Earth. We have some models to do this, but they struggle with predictions at the scales industry requires. For example, physics-based magnetohydrodynamic models can be used to forecast the magnetospheric response to the solar wind, but they do not reproduce the small-scale structures that are important on the ground, and they are also limited by the fact that they approximate the physics. There also exist statistical models such as the Weimer model, based on averaging geomagnetic measurements and the solar wind data. However, this does not provide a dynamic forecast and only produces a statistical representation of behavior. How do we bridge this gap? We have created a data-driven model that includes a large set of solar wind information that can be used to dynamically forecast the large-scale geomagnetic activity. Additionally, we have developed a set of models to investigate the latitudinal information propagation, laying the groundwork for better localized space weather predictions. I'll now hand you over to Vishal to talk about our first model.
Thanks, Theo. Our first model is what we call the global model. There are two parts to the model. The first part is a global reconstruction model, and the second is a forecasting model. We have seen how geomagnetic activity measurements are not available all over the Earth. We have them only at selected stations where the select locations the stations are present. To combat this sampling issue, we summarize the data at each time step across the globe through spherical harmonic fitting using compressed sensing methods. Essentially, we lasso out a set of sparse coefficients from the measurements. We then consider various solar wind parameters averaged at multiple timescales and feed them in through a GRU cell, which sort of summarizes the input into an encoded state. And we then have an MLP, which decodes this information into spherical harmonic coefficients. Once we have the coefficients, we can reconstruct a global map of the geomagnetic activity. And if we sample at the locations where we have stations, we know what the geomagnetic activity at those locations would be. So what do our predictions look like? Hold on to any nuance, and next. You can see the predicted activity on the left, the target on the right. The top row shows the activity over the whole globe, and the bottom row shows the activity at selected stations. You can see from the top row that majority of scales are captured very well, and the global features are captured really well by our model. From the bottom row, we can see that at the location of the stations, the activity is captured pretty well, as in the colors are same. And now we can ask a question. Can we understand how activity progresses spatio-temporally using machine learning? I now hand over to Panos to answer this question.
Our second task is to determine whether we can use information from various stations on Earth to better predict fluctuations on different locations. Starting from a physics-driven hypothesis that the effect propagates from north to south, we conduct an experiment to demonstrate that we can indeed forecast locally in the south using data from various north stations. We feed the solar wind data and data from multiple stations into two separate recurrent neural networks to capture the effect and the cause at different locations on Earth. The output of the recurrent neural networks are then fed into a multi-layer neural network, which outputs 30 minutes forecasts of a target station. It's important to note that past information of the target station is not part of the input. Therefore, we're forecasting the effect on a different location than the input data. That way, we measure how the performance improves by incrementally adding information from stations that are more north than the target station. We observe that as we add more stations that are more north than the target, the forecasting performance improves, suggesting that the information of these stations contain effects that are observed on the target at later times, therefore allowing us to construct a better forecasting model for a station location that we might not even have data from. Overall, our contribution can be summarized as follows. We want to increase our ability at forecasting the solar wind effects on Earth as space weather impacts our large-scale and technological infrastructure. Improving our forecasting abilities helps us employ mitigation strategies. With our work, we provide an improved representation of the global geomagnetic activity structure, but also we demonstrate a new methodology for studying information propagation across the globe. Continuing forwards, we aim to improve our forecasting models by providing more localized forecasting, but also build a surrogate model of the heavy numerical simulation models, motivated by the success of our initial results. Finally, we aim to expand our dataset to cover geomagnetic field perturbations at different altitudes. For example, by using data from other missions like Ampere, Swarm, or future constellation satellites like ones from Amazon and SpaceX. We would like to thank our stakeholders, mentors, and FDL team for providing such an opportunity for us. Thank you for listening.
Thank you so much, Geoeffectiveness team. And I'd like to invite our panelists back to be able to provide a little bit of commentary on your work. So for this round, I'd love to know what's one thing that stood out for you from this presentation. So to start us off, I'm going to go to Rodney.
Yes, so the one thing that immediately stands out to me for this team is that the really compelling results and visualization that were presented as part of this, I think is shaped by the fact that you're pulling from a diverse set of disciplines. You're really calling from the marriage of folks who have expertise in this particular application area, as well as AI ML expertise. And if you're working in either in those disciplines independently, you can only get but so far. When you bring those sort of the intellectual capital that both of those the people who sit in those different disciplines together and rely on AI ML expertise and when to use and how to use first methods based upon first principles in physics, I think that's what's ultimately going to allow innovation to happen. You're operating at the creative boundaries of your discipline rather than at the centers of it. And so that's really what stood out for me, at least, for this particular team, to move us towards hopefully predictions that have a high level of accuracy. Yeah, I'm really encouraged by this.
Thank you, Rodney. And Scott.
Sarah, I think it's echo what Rodney was saying too. I was struck by one thing. Those visualizations were awesome. I mean, I think what they did is such a great job. And I immediately reminded of two things. One, remember Christopher Columbus? And he's exploring. Imagine what he had, if he could actually predict weather. That'd be pretty amazing, right? And I think now we're going out, we'll say we send 30 of these starships to Mars in the next decade, right? It'd be certain, I bet this would be a morning forecast, and I see their visual right there, and everyone's tuned to the their version of television, watching what's happening with the weather that's happening in space. And the second thing is here on Earth, we're all trying to connect the next billion. There's a couple billion minds that aren't yet able to access the internet. And that's going to be largely through satellite. And with thousands of satellites, we need the ability to forecast weather. Super important.
Great. Thank you, Scott. Yeah, maybe we'll have a space weather channel for our astronauts in the future. So thank you. And now we have Aaron, you're up. Oh, Aaron, we are unable to hear you. All right. Bill?
So while we,
yeah.
While we wait for Aaron to reconnect, just building on what Scott said and what Rodney said, this kind of work really could become like a dashboard item, as Scott was mentioning, like you wake up in the morning and you see the forecast. I mean, this could be literally on the
right on the starship. Yeah,
right
exactly. On the starship. Yeah, absolutely.
Really fantastic.
Can I have an app for my Google phone, Scott? Can you make that happen?
Yeah, we'll do. Okay, I'll take that down. And we need to there's a new job, I think, which is a space weather forecast. Right.
Absolutely.
Yeah.
It's really impossible to understate the importance of space weather and understanding it. I mean, no, but you mentioned earlier how vulnerable we are and our technologies are. If a Carrington event happened today, we'd all go dark, and it could be for months. So this kind of forecasting could really prevent that kind of catastrophe. It's really, really extraordinary.
Right. And the physics, Bill.
Bill, that's exactly what I was going to comment on. Yeah, that was exactly what I was going to say. Is hopefully one of the things that struck me was one of the opening comments that was, we can be ready, but I couldn't help but to think in the middle of a global pandemic right now is, we heard we can be ready, but are we ready? And after seeing this, it's hopefully there's so many policy implications for this.
Yeah, totally.
Thank you so much, Aaron. And so now we're actually going to move over to our next Helio team that's going to kind of go in a completely different direction. And that is our Star Spots team.